Okay. I think we can start. Uh, Great. So I think we can start now. Uh, Welcome all to the session 4 of live interaction for the course of Gas Dynamics, offered by Professor Shisha Rao. I am Shri Sahai Gupta. I am serving as a teaching assistant for this NPTEL course, taking the live interaction sessions. Uh, uh, Please excuse me today. I have a sore throat. I was ill for the last week and have not recovered fully yet. So please bear with me with my low voice, and I would be continuously drinking water, taking breaks. So please bear with me for today's session. Uh, the topic for today is gonna be uh, normal shocks, and we'll get started with it for the benefit of people who have not watched uh, videos for the first three lectures. I am Shri Sahai Gupta. I am a doctoral student at ISC Bangalore. My hometown is in Agra, Uttar Pradesh. I did my bachelor's from IIT Ropar, briefly worked in HPCL, and then joined my doctoral degree. Currently, I'm going to finish my fourth year of my PhD. Uh, I've also mentioned my contact details, my website, and my LinkedIn. You can uh, go to these links if you would like. Let's get started. A small recap from the previous lecture would be nice. So let's do that. So a small recap. Let's go ahead. Last time, so we have had three lectures up till now. The first lecture was just a brief overview. In the second lecture, we explored the fact that uh, why high-speed flows imply compressible effects coming in. The second problem and the second live interaction session, as we had nothing much uh, related to gas dynamics as such, we started exploring the power of integral form of governing equations when we want to calculate average quantities. For example, if we want a cumulative effect of something, we go ahead with our integral equations rather than solving for differential equations. That is the idea. Uh, a word of caution there, it's not the power of integral equations and integral form of equations in the integral form alone that allows you to solve for simplify a very complicated problem and solve for it very easily. There are a lot of simplifying assumptions that we take in 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 the way to make progress. So that is one point. Last we looked at a a thrust on of a propulsion device, of a jet propulsion device, and we saw that the force is related by uh, uh, so it's actually like this, and there is additional force term that comes of something of this sort. Now, in this format, it might not give you the physical significance of, uh, I must say, oh, someone is joining, so let's. Hello, Pranav. Hi, am I audible?
Yes, yes,
I guess I'm audible. Let me know.
yes, yes, sir.
Yeah, great. So I think we are just 2, 3 minutes into the uh, recording. I've started recording. I just started recording the video, and we are just 2, 3 minutes into the video. And I've not been keeping well in the last few days, so that's why I have a little sore throat. So I'm gonna speak a little low today. Please let me know if I am not audible. And and also I will be taking some quick drink breaks, just sip of water. So yeah, don't bear with me today. Uh, I was just going through and this recap thing where we uh, derived the expression for the force on of the thrust force on the jet propulsion device. This is something that we saw, and in this form, as we had last discussed, I remember you were there in the last meeting. We had discussed in this format. It does not give you a very physical significance of this expression, as there are some cancellations happening. A more physical, like a more of like a better expression which gives you a physical significance is the one where those cancellation does not happen, and you see that there's a force due to the pressure on the engine walls, and there's a pressure force on the two walls of the engine, the inlet wall and the outlet wall, and there are side walls as well. And so that is something that we had looked at last time. Uh, we could have solved some problems, but that was all to just demonstrate that integral laws help you solve some problems where you need where you need to calculate uh, cumulative effects, right? When you want to know the cumulative effects of something and not the detailed uh, field or detailed variations of some quantity. You want cumulative details, go for integral form of equations, start solving those equations. Anyways, today we are going to do normal shocks, some problems on normal shocks, and we might as well just get started with it now that one of the students are present. I'll just write down the first problem, and then we'll go ahead and start looking at it. Maybe, Pranav, we can have a discussion. How do we go and solve out the problem we're going to discuss today? Before that, do you have any questions of your own you want to discuss?
No, sir. No,
Okay.
nothing.
Okay. So I have selected, I think, 2, 3 problems today. I guess I think you won't be able to see this. Okay. So a pitot tube is placed in an air stream with static pressure of 0.95 atmosphere. Um, calculate the Mach number if the pitot tube measures sorry, measures a measures the stagnation pressure of A 1.1 atmosphere, B 2.5 atmosphere, and C 10 atmosphere. Okay. Have you read this question, Pranav? Are you able to read this question?
Yes, yes, sir.
Do you know how to solve it, or have you seen this problem before?
Uh, I I have a crude knowledge. I don't remember the actual formulas, but I know the concept that the the pressures. Wait. If it is a supersonic flow,
Mm-hmm.
for that we need to. I think we are actually calculating the pressure after the shock.
Mm.
So there is a shock just before the inlet of the pitot tube. So
Yes.
we calculate the pressure after the shock. So we need to calculate the pressure before the shock. So we need those ratios and all. So I don't
Okay.
remember.
You have gone through this problem. You know about this problem. Good.
Um,
And also we need to. So you're saying we need to. Great. Uh, okay, fine. Now, just to motivate the solution, you upfront mentioned shock. Why do you think? Why did you need to bring shock into the picture? Is there a reason for it? Like, how did you know? Like, for example, if this if, does the fact that we are in a gas dynamics course, does that make you talk about like suggest that there is gonna be a shock in somewhere, or is it very fundamental to any problem, any pitot tube problem? Like, do we consider shocks in fluid dynamics when we solve similar problems in let's say second
no,
year of
no.
fluid dynamics?
Sorry, I didn't actually talk in the general sense.
Hmm.
Actually, we need to see if there is a shock is there or not.
So that's
So
also
if
great. So I'll write it down.
yeah,
We need to see.
yes,
Great, great. Okay, but great. So you said that this is a more general statement, right? You said this is a more general statement. I'll
yes.
write
Firstly,
that
we
down.
need to
So
see
this,
that
uh-huh.
if there is no
Okay,
shock, then the when we can directly check the pressures.
great. But why do you suspect shock to be present? And you also mentioned, let me write that down too, that if the flow is supersonic, like I know that you now that you know the solution, it might be very trivial, the questions I'm asking, but for the benefits of your fellow people who might be coming across this for the first time, it becomes a little critical to emphasize the fact that there can be a shock upstream of a pitot tube. So let's discuss that as well. So that is why I'm gonna say I'm gonna say that if the flow is supersonic, there might be or there will be. Tell me that. Is this might be correct? There might be a shock present.
If if the Mach number is greater than one, I think
Which
greater
is
than
the
or
flow
equal
is.
to yes. So if it is if it crosses the M Mach 1 mark, then
Mhm.
we can see shocks, but there may be a, there may be shock. I don't know. It's depends on the
Interesting.
Mach
Great.
number.
Great. So you're saying it can be a weak shock, it can be a strong shock. Great. Great. Shock or a strong shock. Right? That is what you're saying, right? And I'll put
Yes,
it
yes.
this question in hindsight or as a I don't know, um, like a teaser. Can we uh, have a subsonic flows? I guess you can answer it very fast. What do you think? The sixth question. 6 point.
Mm, no, we cannot have subsonic shocks.
No,
Cannot
we
we explain
cannot.
it?
You can't explain it. Okay, let me write that too.
Mm,
Can't explain it. Hmm.
no, no, I am
But
not
no, the
personally.
point
I am
is
not
no,
able to.
no, no, no. I get it. That is a very interesting thing for you to say. I'll tell you why. It's interesting because it means so at least you'll learn something new today. That is we can actually show why this there is a proper reasoning why we cannot experience shocks in subsonic flows. So at least these parts, I guess you might be able to figure out. But this is possibly something you might learn today. So it is good. That is what I. So anyways, try to answer the seventh question. What do you think? Why does it not happen? Whatever your intuition says or whatever your first thoughts are, that's okay. We are not the only point of this discussion is to just motivate the rest of the lecture so that that goes in a story rather than me bringing up these points later on. I am jotting them down today together, and then we'll move on following these points so that we'll have a flow. So you can try to answer the seventh question, whatever you think.
So
Why
right now,
shocks are right
okay,
now,
okay.
whatever are your first thoughts, yeah.
Sir, I think it's because if it is subsonic,
Uh-huh.
uh, um, I'm able to process it, but I cannot put it into words right now.
Are you gonna say something about disturbances and the propagation of disturbances or something? No?
I was actually thinking, yeah, yeah, the propagation of disturbance, because we cannot, the information can travels at the speed of sound. So
Okay. But was this line of thinking the exact one what you were thinking, or was it something else? You were thinking
I was
something else.
actually thinking about compression waves. So
Compression waves. Okay. Okay. So you think
mm,
compression waves don't exist in subsonic flows?
okay, I
It's
need.
okay. You can choose to not answer. You can say I don't know. I don't know. You can simply say that.
I think I should not answer it
Okay. So
right
it's
now. Uh,
yeah, it's okay. So yeah, because now it's becoming too much. There are too many questions. Like I'm questioning you too much. So it's okay. The point was just to try to understand what are the first thoughts people have when I say shock in a subsonic flow, and by just looking at this expression, if I were to make a statement out of it or complete it for you, I would have said that compression waves don't exist. Those. Okay, so we'll look at it. This is something out of the scope of what video lectures you have looked at and what I'm going to discuss today. But anyways, there is another way to look at it, and that is the thermodynamic way. And we'll look at it again later on, but first we'll solve this pitot tube problem. Uh, okay, fine. Now, if the flow is supersonic, there might be a shock present. That is fine. One more question to you is why? Why a shock would be present in a supersonic flow with a pitot tube in it? It's a fairly simple question, not very. Uh, it's a stupid question, I must say. Yeah, but it's critical for someone who would look at this problem for the first time. It might confuse him. Yeah.
It's I think it's because of the contour of the front contour of the pitot tube. So the 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 flow tries the flow collides on the surface, and due to that there are waves which propagate in the opposite direction. So I think that's why. I think so.
Okay. Okay. Great. So I think okay, fine. Let me try to answer it again. Well, let me just see if I can draw the how a pitot tube looks like. So pitot tube. Well, let me grab a picture from internet and then put it there rather than drawing it myself. Right. This is a good image. Copy image. Fine. So the what you said was more or less correct, but it's not fundamental. Uh, well, yeah. So now I'll show you what is the fundamental reason why there will be a shock wave in supersonic flow with a pitot tube. The reason is that there is a stagnation point at the nose of the pitot tube. So okay, I'll come here. So the thing is that you have a pressure tap where you are measuring the static pressure. Here the velocity is zero because this is gonna be a wall. So suppose there is a plane. Okay, let me because right now the way we are talking, we are not. This image shows internal flow, right? The flow is internal in a pipe or something, which might confuse you because we have been dealing with only flows away from boundaries, away from walls. So it might confuse you as to why we are looking at flow in a pipe right now, but it does not matter that much. I'll show you. So in this image, yeah. Oh, what is this? Yeah. So in this image, you see this is an external flow. Okay. Even in this one, there will be some pressure taps on the wall of this aircraft. And similarly, at the wall, you can expect the velocities to be zero. So this one measures the static pressure. Here, oh, what is this? Oh, wait. Yeah. So were you able to see that screen? Right. Let me do. Yeah. So I'll draw it again here. Right. So I was saying, just give me a second. Yeah. So I was saying, see, there will be some pressure taps on the wall of an aircraft or something. If there is gonna be an external flow, even then there is gonna be an object around which there is gonna be a flow. So on the wall of that object, you can still measure the static pressure because on that wall, because of friction, the velocity is gonna be still zero. So it's not like that in high speed flows at the wall there is gonna be a slip or something. At least not in typical cases. not in cases of engineering relevance. That does not happen. And you can very well expect the flow to be velocity to be zero at the surface. And then you can measure the static pressure. And the pitot tube then measures the stagnation pressure also by means of isentro isentropically putting the fluid at its nose to the rest. Okay, so this becomes a stagnation point, and there you measure the stagnation pressure, and then you subtract these two pressure values to get the dynamic pressure. That is how a pitot tube works. Okay, that is the logic of pitot tube. Now, in the attempt of stopping the flow to its velocity zero, something that is happening at the boundary, naturally, the flow there itself is of zero velocity. So that is static pressure, but there's a high speed flow incoming which gets decelerated to zero velocity at the nose of the pitot tube. That is something what Pranav was also talking about, that because of its shape, you're gonna have some uh, what do you call this displacement of streamlines. Let me just draw this more nicely, otherwise it becomes flat. Yeah, so something of this sort. So there will be uh, I guess symmetric streamlines, but there is going to be one streamline which is going to touch the body, the pitot tube. And this, as we have also looked at ideal flows, right? The body of anything, any external body itself becomes a streamline. This is the zero stream. This is zero velocity streamline. Like in a sphere also, this itself becomes a streamline, right? And there is a stagnation point here, right? I don't know if you are able to recall this thing or not, but you can go and check about this. So, anyways, the thing is that because pitot tube is decelerating the flow to zero velocity, a supersonic flow is gonna decelerate to zero velocity, and you cannot expect that to happen while remaining in the supersonic regime. So the flow is gonna go into subsonic regime. Okay, and the way supersonic flows decelerates to subsonic to subsonic regime is by way of a normal shock. Okay, so in high speed flows, when pitot tubes are there, we experience normal shocks. Okay, that is the case there. I'll just take some water. uh, I'll just take some water. uh, I think I guess it's this one is a little bit clearer now. Uh, Now this becomes a little bit just simple, very simple. So we'll look at it now. Uh, Fine. So let me see if I can draw a drawing or something, and then we'll move ahead from this. We'll solve this problem. One more thing that I will do is take this. Yeah, right. So let me see if I can draw. Yeah, right. So suppose this is the pitot tube. Please excuse my drawing. And right now, I'm not gonna say if there is a shock or not anywhere. I know that the pressure tap away from this pitot tube measured the static pressure to be 0.95 atmosphere. Okay. Now it says that the Mach number, uh, if the pitot tube measures a stagnation pressure of 1.1 atmosphere, uh, what is the Mach number? Okay. So now, uh, can you guys tell me the general expression for for the stagnation pressure and the static pressure? Suppose, let's forget, and suppose if there is a shock, let me draw a shock with a dotted line, emphasizing that it might exist, it might not exist. As we have discussed, that we are not sure if it is going to exist or not. We are going to see about that. we're gonna figure out a way that see, there must be some way to oh my God. So the point is, suppose there is gonna be a shock there, okay? There is a shock or not, or there is also another way of developing a method or developing a analytical formula or something where existence of a shock or not does not affect the result. Okay, so we'll see what am I talking about. Basically, the same equation will give you the result despite the fact that there is a shock or not. Okay, so we'll see that. Anyways, uh, suppose this is the pressure we measure, and I'll write it as 1, as conventionally we have been doing, and 2 here. So I know that these values are P naught 2. Okay, and suspectedly, this is P1. Do you guys agree?
Yes.
Right. Now, let's break down this problem and start looking at uh, the fact that if P naught 2 is known, can we at least go ahead and write an expression for P 2, not P 1, but P 2 as a function of something? Do we know a formula for it? Basically, static
Uh,
pressure from stagnation pressure. Yeah,
so P P naught 2 would be P2 plus half rho V2 square.
P naught
So
2,
like stat
P naught 2 will be P2 plus half rho V square. Let me use U right now, rho U square. Okay, and U2 also there, and rho 2 also there. Okay, so that so this is what you're saying, right?
yes, yes.
Ah, interesting. Okay, uh, are you sure about this?
Sir, we can take the isentropic relation.
Ah, okay. Okay, so please tell me how do we do that, and who is this? Would you like to tell me your name?
Sir, I'm Deepthi.
Hi, Deepthi.
Um,
Yeah,
Hi, sir.
yeah. Go ahead. You can introduce yourself.
I'm Deepthi. I'm from Kerala in the district of Trivandrum. I'm a PhD
Okay,
scholar in the area of rocket propulsion.
okay,
So I can't able
okay,
to attend the previous classes. So today I'm
okay,
starter. I think
okay.
it's a
It's
good for
good.
to interact you.
Great, great, amazing. Yeah, Deepthi.
Mm,
Great. So
mm.
you're saying there is another way. Yeah, go ahead.
Yeah, it's maybe I'm not sure. It's
Mm-hmm.
maybe since it is in the I think P naught one is equal to P naught two.
Ah, okay. Okay. P
Uh,
naught 1 equals to P naught 2. Okay.
two.
If
So if
can we say that this means that there is no shock, or can we say that in spite of the shock present,
yeah,
is
we are
shock in
considered
ison?
as an so
Ah, if
if
we
we
consider, okay.
consider either shock, either it's an isentropic relation,
Ah, okay. So if we consider it as an isentropic process,
entropic
then
relation.
this. Ah, okay.
Mm.
Amazing. Great.
So
Okay.
P naught one by P1, there is a isentropic relation that is 1 plus gamma minus 1 m square the whole raised
Great.
to gamma by gamma minus 1.
So P
So
naught
from
2
there we
divided
can,
by P2 is there. There is an expression. Yeah, go ahead. You tell me
yeah,
the expression. Yeah, 1 by
1 plus
um,
gamma minus 1 by 2
yes,
m square the whole
yes.
power gamma by gamma minus 1.
You sure about the exponent? Because I
Gamma,
am not. I'm gonna check it. So gamma
yeah,
minus
I'm
one. Yeah.
the gamma.
I'll also
So
check
we
it once. Uh, yeah. Yes.
have
Okay. Great.
so
Great.
since we are find out the calculate the Mach number. The
Yes.
stagnation pressure is also given, and we have P1 also.
Okay.
Uh, and P01 is equal to P02. From there, we can find out the value of M.
Okay. So Deepti has raised 2, 3 points which are very important. I guess let's jot them down.
Hmm.
Uh, but Deepti, I would need and so basically you're saying now that we know that P01 equals to P02, we can substitute it that there, put in the
Yeah.
values, find M. So Deepti, there's one thing which I just uh, compensated for, which I should not have. What is this? Will this be M1 or M2? You're not sure? You
Hello.
can say that as well. Hello.
Hmm.
So did you
Yeah,
did
sir.
you hear my question? The question was, uh, in this
Hmm.
formula, is this M1 or M2?
So M1.
M1. But
That,
why do you
that is
say
not
that?
P not
Why?
1 by P1.
So this is P not 1 by P1. Okay.
P1.
Okay, fine.
Hmm.
But now we know P1 and we know P naught 2. So, and you're saying P naught 1 equals to P naught 2. So we can find out M1. That is your
Hmm.
logic, right? Okay,
Yes,
great.
sir. Yeah.
That is good. That is good
Hmm.
from you. See, Pranav told me
Hmm.
this expression, and if I divide this expression by P2, or let's say we write it for P naught 1, just like how you've asked me to write it for the other thing. If we do that there, let's do this
Hmm.
and divide both sides by P1 so that we get a similar expression both on like
Yes.
ones. So we are going to
Hmm.
get what? This is P1. Now let's apply ideal gas law because again we're gonna look at only ideal gas in this course. What is rho 1 by P1? It's gonna be 1 by RT, I guess.
RT. 1 by
1
RT.
by
Yeah.
1 by RT. Okay. So let's substitute that. Uh, so 1 by RT. This U1 square can be written as something else so that we can get it in Mach number.
We can get gamma multiply and divide by gamma, so we can get
Yeah. So
sonic.
basically Mach square into speed of sound. I
Yes,
guess that is what you meant. So M1
yes, yes,
square,
yes.
M1 square, then gamma RT. So gamma gamma gets cancelled and this becomes gamma, right? This is gamma. Should I do it properly? Wait, let me do it properly. RT. This is RT. The U1 square gets Deepti, is this fine?
Yes, sir. Yes.
It's fine. Okay. So RT gets cancelled and we have with us this expression. Okay, let me put gamma up there. Now the problem I'm facing is, are these two expressions equivalent? And how come I don't think Pranav was wrong anywhere, was he? When he wrote this expression and you told me this expression, how are these two expressions not the same? Or where is the mistake? Is Deepti doing any mistake or is Pranav doing a mistake? Or you think both expressions are actually equivalent if we go ahead and solve it? Let me ask you a question. Nobody wants to answer that. Should I go ahead and try to answer it for myself?
Yes, sir. Yeah.
Okay.
Yes, please.
Hmm.
Hmm. So, uh, I guess Deepti got this expression from the gas dynamics book or somewhere like from the video lectures or something. Where did Pranav got his expression from?
Uh, I don't know, but I know that if the flow comes to a stagnation, that the v becomes zero, that means the
Ha.
dynamic pressure gets converted to static pressure, and then we
But
get
ha.
the stagnation pressure. So
Okay. So now,
summing up those values, yeah.
okay. So now there's an
That's
interesting
a
catch
Bernoulli's
here.
equation also.
Okay. Well, in fact,
Yes, I think.
she's correct. This comes from the Bernoulli equation itself. So correct. Okay. Great. Very good, Deepthi. Now, she says that this definition of static stagnation pressure comes from Bernoulli equation. Now you tell me, have we used Bernoulli equation in our when we derived this? Have we used Bernoulli equation? Well, let me ask you this again. What is Bernoulli equation? See, we have three governing equations. Okay, there is only three ground truths.
Bernoulli's
There
equation is
is
from momentum
uh,
equation. Momentum equation is a form of
okay,
momentum
great,
equation.
great. So Bernoulli equation comes from momentum equation. Do you know what momentum equation is used to derive this Bernoulli equation? I guess
Yes, yes. While undergoing some assumptions, we derive this equation from momentum equation.
well, it comes from yes. Yeah, so okay, fine. So again, so she answered my question very fast. The point is that Bernoulli equation comes from the momentum equation. The thing is that the momentum equation in the this momentum equation you have looked at, or this Bernoulli equation you have looked at in the fluid mechanics course, in the incompressible regime. What is the momentum equation in the compressible regime? It's different from the momentum equation in the incompressible regime. That is what I want to emphasize. So, can anyone tell me the momentum equation in the uh, incompressible regime? What is it? It's something of this sort. Let me write it down. It's I'll consider all the assumptions that we have done when we. Okay, first let me write it for the compressible flows. Okay, compressible flows. In the compressible flows, we took some assumptions, right? We took what assumptions? One dimensional flow. We took steady flows and all that, and we write P1 plus rho 1 U1 square is a constant. Pranav, is that okay to you? Do you need me to derive
Mm,
this?
no, no, it is okay.
You can go ahead, go and look at it. Okay. It actually gets you can actually derive it. Okay. It gets derived that way if you look at it. Okay. Now, I'll show you the incompressible momentum equation. There's a catch there. We'll actually witness why these two expressions are different. So we'll see that. So now in that one, it's something of this sort. U du plus dp equals to 0. Now it might look to you that this is some very weird form of incompressible equation. So you'll think I have not seen this form. So let me show it to you what I mean. It's generally rho du by dt. And again, the assumptions, the same assumptions that we had taken for the compressible flow case, we'll take it there, one dimensional flow also. Um, this makes it to be my throat is a little bad today. Bear with me. Sorry. Um, there are not gonna be any viscous forces. That is one of our assumption. The flow is gonna be steady. So this breaks into U, the same thing. one-dimensional flow, so the other components get cancelled. You guys agree with me? There is some mistake I'm making. I think this is fine. Yeah, mistake is this. Okay. Now, yes. So this is fine. So we can write it to be here. Okay. Now because this it's only one dimensional, I can just remove dx because it's one dimensional, right? There is no other coordinates. The only variation is going to happen in x direction. So we can just simply write du's, right? Rather than it's the same thing. See, it's the same equation. It's just dx is removed from both of it. You get it, right? This equation you have looked at. Does this make sense?
Yes. Hmm.
Okay.
Yes.
Now, in the incompressible regime, because rho is more or less a constant, only rho can go inside without getting differentiated or anything. This becomes p plus what will it be? Rho u square. Do you get this? Because rho is a constant. See, I actually removed it, which is a very bad idea. Let me write it again. We are able to see the screen, right?
Yes, yes.
Yes.
Now, because rho is a constant, it will just simply go inside the derivative. It will not get any, there will be nothing to it. It will remain invariant. U will go outside and it will become u square by 2, right? Does that make sense as well? You see the first expression and the second expression. If the density is a constant, more or less. No? You can say no to me. I'll remove this drawing and all. Does not make sense?
No, it makes. Sorry, I didn't
There's a
get. I
there's
think
a
I think
doubt.
I lost somewhere. No, no, no. I lost some sound in. I don't know, somewhere in
Okay.
the last few
I'll
seconds.
repeat myself. I'll repeat myself. I'm saying because rho is a constant now in incompressible flows, rho can when you take it inside the derivative or you take it inside like this. In here we also can do it. So let me do it there as well. That can also be done. Wait. So let's look at this equation again. It's not a big deal. See here, I'll take the whole thing inside and I'll write it like this. So you let me know if this is okay or not.
Yes, yes,
Right? This makes sense.
yes, yes.
This is exactly what Bernoulli equation is, right? P plus rho u square. If you have some potential term also, where in the case you'll have a potential term here, like right, plus or minus rho g or something, rho g z or something that will also get inside. So you get the full Bernoulli equation. It's the same thing. Okay. The catch is that rho is taken as a constant. Only then this becomes rho u square by 2. The same equation, this equation or this equation, when rho is not a constant, it it comes out to be like this. It's p plus rho u square rather than p plus rho u square by 2 is a constant. Okay, so that is an important catch. So, and you can agree, right? Compressible flows and incompressible flows will have different momentum equations because density is not remaining constant in one case and it's varying in the other. Sorry, it's a constant in one case and it's varying in the other. Makes sense right now or no?
Yes, 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 sir.
Yes.
Great.
Yes.
So I'll move ahead. Yeah. Now, now let me also show you that in the limit, uh, compressible effects are not important. It should happen. that the expression we got from this equation, uh, see, we got this expression. Oh, this expression from this equation and this expression from this equation. In the limit Mach number goes to 0, which is the limit of incompressible flows, this should reduce to this case, isn't it? That should happen. That should naturally happen. And that is part of the problem I wanted to discuss with you. So we'll discuss that. Okay. Shall I move along? Yeah. So let's do
Yes.
that. Great. So yeah. Okay. Let's go ahead. So now I will remove one and all so that I don't have to write. Right now we are just seeing the relation between stagnation pressure and static pressure. Okay. So one and all I'm removing because now there is no position as such. Okay. Now the way I'm gonna do it is take a log of this. And because we are, see, basically there's an expression and we are solving it in the limit Mach number goes to 0. That is that is simply mathematics, nothing else. Okay. We'll take log, okay? If we take log, then we get this expression. Okay, let me take ln. Log and ln is the same thing, but mhm, ln is this expression. Uh, so does anyone know? Can we expand this ln term further? In the limit m square, m goes to 0 or m square goes to 0 is the same thing. So it does not matter to us. You're still able to see the screen, right? Let me just increase the font size also a little bit. So I'll tell you the expression. Uh, ln of 1 plus x is equals to x minus x square by 2 plus x cube by 3 and so on. Okay, something of that sort. Uh, so just like that, we'll expand it. Okay. So what are we gonna get? We're gonna get plus minus into, yeah, dot. I'll put dot to modulus. There is plus, yeah. Oh, it's a stupid idea like that. Wait. And so on. I'm not writing the third term, although I should. But anyways, and you see some cancellation also happening. So let's go and do that. So now you can see that it's simplifying, and already that now that we have discussed, we expect that the two expressions will, the limit, the first expression will converge to the second expression. So taking this inside, you get gamma by 2, right? Get gamma here. That's it. Now, and so on, right? You get this, right? Wait. Is the issue or what? No, it's okay.
Yes.
Fine. Right. Now you see that this term is an order of magnitude lower than this term. This is the most dominant term in this series. Right. Or let's
Yes.
let's let's
Yes.
Yes,
yeah, let's keep this.
yes, sir.
Let's keep this term. Let's keep this term. Let's not remove these terms. Or maybe let's remove these. Let's not remove these terms. Let's see. There is a little bit more to be done here. Okay. But you can see something is gonna happen. Something is already happening here. Okay. So now you see we'll take the ln out. This thing we'll do so that we can write p naught by p. Oh, oh, this will become e to the power, right? This whole big expression,
Power.
yeah, right? This is okay.
Yes, sir. Yes.
Right now again another expansion of e to the power x. So e to the power x, you guys know, is gonna look like this: 1 plus x square by 2 and so on. So now when I put it like this, we get p naught by p. I'm not writing the limit part now. It's gonna be 1 plus gamma, this term, and so on, right?
Yes, sir.
There
Yes.
will be other terms also. Again, now in this case, I will remove this m square wala part. I'll say this is now not this is gonna be a very weak term. This is the thing there. Again, multiply p on both sides so that we get p naught. Sorry, we get p naught and p, uh, and this becomes gamma p. Right now, p can be written as rho rt. So rho rt, gamma rt, is a square. A square m, is u square, and that's how you get this in this limit. The two expressions are okay, but it is only in the case in only when in the limit Mach number goes to 0 that you can use this definition of stagnation pressure equal to the dynamic head and the static pressure. Now, uh, it's actually important because the definition of dynamic head is actually half rho u square. It's the definition of dynamic head is not P naught minus stagnation pressure minus static pressure. Okay, dynamic pressure uh, see in in high speed flows, dynamic pressure is still half rho u square. Static pressure is static pressure in both the cases, but stagnation pressure is not dynamic pressure plus static pressure in compressible flows. So just remember that. Dynamic pressure is still half rho u square even in compressible flows. The definition of stagnation pressure changes. Okay. That actually is coming from the
Okay.
fact that stagnation pressure, you have to isentropically decelerate the flow, and that is the actual definition. The definition of the definition that it is the sum of static pressure and dynamic pressure is a derived definition. It is not a general definition. Okay.
Okay. Understood.
Oh, fine. Uh, this is okay. So where were we? Let's go back. Where were we? So this was a little digression. I wanted to just show to you how this comes. Now, this is fine. So now at least we know what the stagnation pressure and static pressure is. She just told us straight away. Now, Deeply, maybe you missed that discussion. The discussion being that in supersonic flows, you can get shocks in front of the pitot tube, upstream of the pitot tube. Do you know why?
Sir, it's breaking, sir.
Okay. It's okay.
I hear
Maybe
that
if
supersonic condition. I heard only
So
that the supersonic condition
the
is of
question is
shock.
that we had a discussion that uh, in the case of supersonic flows, there might be a shock present uh, upstream of the pitot tube. So do you know? Are you comfortable with that statement? Do you expect that to
Yes, sir.
happen? Oh,
Yeah,
okay,
yeah, yeah.
fine. So we'll move ahead. So now given that there can be a shock upstream of the pitot tube, now what do we do? Okay. See,
So
another
in
interesting.
case of supersonic
Hmm.
condition, sir, can I? There is another equation. There is a Rayleigh-Pitot static tube equation.
Mhm.
So we can, in case of supersonic conditions, I think we take that equation instead of this. Then
No, but
some
what is
there is
that
some
equation? How is that equation derived? What is that equation? Like what is the logic of that equation? What is that equation? Where is that equation coming from? I'm not asking you to tell me the equation. Where is it coming from?
that I had studied somewhere in case of the
Uh,
supersonic flow, we can't able to use
uh,
this equation instead. So we can't predict that either it is a total pressure.
okay. So there is
Whether,
a better way, I guess. Okay. Okay, understood.
yeah.
But I've not gone through it. Maybe I can do that too.
Oh,
I'll go through it. Uh, uh, maybe we are gonna do the same thing, I guess. I think there is only one way, and that is it's just that I don't know the name of it, I guess. But anyways, one more important thing is, see, how do you calculate Mach number downstream of a normal shock? Let's say, Pranav, you tell me. We solve for these equations, right? We solve for those three equations, rho u equals to constant, or let's say, let me write this down, rho 1 u1. So those are the three equations, right? That is how we solve for the normal shock, right? How do we solve that? What are the governing equations which we use to solve uh, the Mach number, the relation between m1 and m2? These are the three equations, right? The momentum equation, mass.
Yes. Sir, are
So
you
you're not
writing
seeing the screen.
anything?
Sorry.
Huh.
I just noticed. So when we are solving for m1 and m2, uh, uh, like Mach number before the shock and after the shock, how do we solve for it? These are the three equations we use, right? Momentum equation, mass equation, and energy equation. I'm not writing all three of them.
Yes.
Okay. So the result, what do we get? Uh, we get m2 as a function of m1, right?
yes.
And generally we have a
Yes.
table out of it. What is the trivial solution of this function? You think about it. The question is, I pose the question that what is the trivial solution to this function? No, nobody can think of anything. Do you know what a trivial solution is? Which is straightforward. We can just without solving anything, without like just straightforward say this can be a one solution to it. These three equations. These are the three equations. Can you tell me the most trivial solution to this problem?
Do you mean the direct formula or that means the relation between M1 and M2?
Direct relation between M1 and M2.
So that's, I think, it's M2. M2 equals 1 plus gamma minus 1 by 2 M1 square upon
Ah,
gamma M1 square
but where are
that
you? Where?
relation.
How are you saying that? What is
Sorry,
the basis of? What is the basis of that?
I think we derive it from the Prandtl
Maybe
relation.
that is what I'm saying. So a solution which you can just see without even touching the pen. Is there a solution to these three equations? And you can just tell me without even solving these equations or deriving anything. Isn't M2 equals to M1 a trivial solution to it? Isn't it? There is no shock,
Ah, okay. Yeah, there is no
right?
shock.
Yeah.
That's it. Yes.
H1 equals to H2, U1 equals to U2, P1 equals to P2, ρ1 equals to ρ2, and all these things. So this only just simply using this fact, we can just go ahead and solve this equation. The fact that if there is a shock and or if there is no shock, we can still use the same equation and go ahead with it. Okay. So let me see how do we solve it. Okay. Let me just see. It's done. This is fine. Okay. So now, so let's assume that we have a shock. Okay. Wait. No. Next slide. So assume we have a shock, and by assuming that we have a shock, it is also possible to not have a shock because M2 equals to M1 is also a trivial solution to that this normal shock. Okay, and we know P naught 2, we know P1. Now we need to find M1. That's it. That is straightforward. That is what we need to do. Okay. So first of all, how will we do that? Is use the normal. We're gonna use the same expression that we wrote just before earlier. Let me just write that. Oh, this. Okay. So because we know P naught 2. Okay. So I'm gonna use this expression. And now in the case that there is a shock, so then we are gonna write P1 by P2. That is our strategy. Now once this is done, there's an expression for this. I guess one of you can tell me. We multiply these two. Uh, what do you say? Okay. One more thing is there is also an expression for M2 in terms of M1. Again, from for the that comes from the normal shock relations. You multiply these two orders, these two ratios. You get P naught 2 divided by P1. So you do it smartly. You cancel out P2. That is what you want to do, which is gonna be P2 times P2 by P1. Okay, now what? And this comes to be an expression of as a function of M1, right? Do you agree? Now
Yes. Yes.
the plan is to substitute. So to first of all find this whatever. Okay, so let me change this to be G. So find this G. Okay, to find this G, plot it because this is gonna this you see this is an implicit equation or transcendental equation. This is well, it's not transcendental. That's an implicit equation. It's not like we are getting M1 as a function of P naught 2 by P1. Okay, it's an implicit equation, so we can do it graphically. We can solve for it graphically. So we're gonna do it graphically. Okay. So now and the plan is now that we know P naught P P1 and we know P naught 2's, We're going to calculate these ratios, uh, see for what M1 these values are gonna uh, come, like where is the intersection gonna happen. So now maybe Deepthi, you have an access to normal shock wave relation or not? If not, then I can just look them up. Maybe I'll
Yes,
look
sir, I
them up.
have.
Wait, you have. Great. So go ahead and tell me what is P1 by P2.
P1 by P2.
Or P2 by P1. That is actually better. So
Uh,
wait, P2 by
uh,
P1.
P2 by P1 is equal to 1 plus 2 gamma
Yes,
by gamma plus 1
yes,
M1 square minus into M1 square minus 1.
great. Do you also have an expression for M1, M2 as a function of M1?
Yeah. M2 square is equal to
I M2 square equals to
1 plus gamma minus 1 by 2
1 plus 1 plus gamma minus 1
minus
by
1 by
2.
2 M1 square
Yes, give me a
divided by
second.
the whole
Square.
divided by
Okay, okay. Whole, is it?
yeah, the whole divided by
Okay, got it. Yes, divide by
gamma M1 square
gamma.
M1 square
Okay,
minus gamma minus 1 by 2.
okay, great. So this is the expression, right? I just asked you to write it so for the benefit of other people who might watch this video later on. But it's okay. I have already plotted this same thing there. I'll show it to you. So wait, let me remove this first. There is my cursor. Okay. So now that we have this expression, we just need to multiply these. You see, right? You just need to substitute M2 in this wait. So you need to substitute this in this formula and multiply these two to get this g of m1, right? So let me show it to you. I've done it. How do we do it graphically? Let me show it to you. Okay.
Sir, I
Let
have a
me change
doubt.
this.
Can I?
Go ahead. Great. Go ahead.
Sir,
You can
either we
see the
not
screen.
know.
Great, great, great. Yeah, go ahead.
Yes, sir. Sir,
Go
we
ahead.
can't know which Mach number this is happening. Either it is in a subsonic or supersonic condition. If
Mhm.
so, how we can directly write this equation that P2 by P, the normal shock relation here?
You are right. You are actually right. That is not going to happen. So I'll answer that question in just a second. Okay.
Okay,
In
sir.
just a second. See, the very interesting thing is that this there is a actually a very good point. Interesting, very good point. I actually made a mistake while writing this. Actually, you're totally correct. So let me write that down. She's totally right. That is what I meant to say. So this is what we are gonna do now. Right. Just give me a second. Okay. I'll just
Okay, sir.
yeah. I'll just wait. Oh, just give me a second. This one is a little. It's a little tricky to write this in the equation editor. That's why I'm having a little trouble. So actually, now you tell me if Mach number M1 is greater than 1, then we can write this expression. Is that okay?
Yes, sir. Yeah.
Right? In so it means that we have to and in the limit Mach number is less than or equal to 1. Then what do we do?
It's no problem. Less than or equal to 1. Less than,
Then
I'm not sure, sir. Less than or equal to 1.
does it
If
matter?
greater than,
The greater
I think
the greater one. Just give me a second. I'll fix this. You tell me.
less than or equal to 1 means we can't able to take the normal shock relation, right?
Right. But then what happens? What is M2 equals to? Does it not mean
Yeah.
it's I'll tell you. I'll tell you. It's
Okay, sir.
simply M1. So simply M1, right? Because there is no
Hmm.
shock. So Mach number is not gonna change.
Hmm.
Is that okay?
Yes.
Right? So we are gonna use this expression, this function, rather than simply putting that formula, which is totally correct. This is totally right. This is how you do it. Okay? I'll show it to you now. Wait. So uh so the way we do it, this is a website. I have used it a lot of times. This is for graphical purposes. It's very nice. See, how do I write it? I have written M2 as a function of this. Same thing. G is the gamma here. See, 1.4 for air I have taken. When it's between 0 and 1, you simply put it as x. X is the M1. Okay, so x is the x-axis here. You're gonna plot this function as f of x. Okay, is x is the M1 and y is f of x. G of x actually. We had written g of m1. So in the limit, in the case when g is equals to or greater than 1, this expression we are going to use. And see, this is how it looks like. So in the limit, this goes to if we had taken only this thing, this was the erroneous part. Okay, if we had not included this. Wait, something. So let me show it to you how this would look. See, it would look like this. Okay, but we know that below m1 equals to 1, this is all erroneous. It does not make sense, right? At least right now we know that. So instead, we do it this way. This is right, fine. Now this is all okay. We move ahead. See, this also 1.1 is this curve will meet 1 comma 1. Okay, so at Mach 1, the downstream Mach number is also 1. Now, the two ratios are also, so this is I think this is P2 by P1. Uh, and I guess that's, I think, yes. So this is P2 by P1, and this is the overall thing. Okay, this is the G of X, G of M1. Okay, now you can see my screen, right? You can see all this Desmos web page and all.
Yes, yes.
So this is the case A. Where the stagnation pressure was 1.1 atmosphere and 0.95, you find a Mach number of 0.46. Okay, so the case A was a subsonic case. You see 0.46 is the Mach number you're getting. Uh, if it was the case B 2.5, you'll get a Mach number higher than 1 because the pressure ratio is of 2.63. You see, earlier the pressure ratio was only 1.15. So again, you can expect it to be subsonic. But see, now the pressure ratio is increasing beyond 2, and now the corresponding Mach number is 1.27. Look at this expression C. I'll open this one again. See, the third one, 10 atmosphere. What is the pressure ratio here? Almost of the order of 10. We almost expect shock to be present, right? It's a high pressure ratio. And accordingly, we will see the Mach number will also be a little higher. What is the Mach number? 2.79, 2.8. So this was the problem. Okay. What else did I need to tell you? That's it. Okay. Something which you can do is see uh, how much error would you get in calculation of the Mach number uh, if you forget all this and just simply use p plus rho u square by 2, or you forget, or you use. So let me get back to the slides. So without doing all this, if we simply use uh, this is something which you can try to just get a feel of what is going on or how much error you might be dealing with if you just don't take care of things. Uh, Consider if you take two scenarios, one in which you use this equation simply, and in the other you use this equation again simply, and solve for the Mach numbers. Okay, so what will happen is in this case, what do you think? What will happen, guys? Wanna discuss that? Are you gonna get any error when the flow is subsonic with these two formulas? See, there is no shock in case A, uh, normal shock in this case. So this will give you the accurate result, isn't it? So this one will be okay. Uh, I guess. How do I let me do it this way? Compressible or Bernoulli. So in case A, this would be fine. What about Bernoulli? Will there be a large error or will there be zero error? What will it be? 0.46 was the actual Mach number. What do you think? I'm telling you the Mach number is 0.46. Now, what do you think? How much error are you gonna uh, incur if you just use this one? I'll tell you not much, not very large. Okay, because zero point 0.3 is itself the limit on incompressible flows, and you're gonna get some error, obviously, but it will be little small. In case B, where the Mach number is 1.27, what will happen here? It will again give you a very small error. Okay, small error. There will be a small error. But with this one, you're gonna get a supersonic Mach number. Obviously, you're gonna get a supersonic Mach number if you use this in the case B, which I don't know how do you explain it, because this itself is a subsonic uh, formula. So I don't know if it's even allowed to discuss the possibility of an error, possibility of how much error you're getting. Because if you're using this formula, you should be getting a subsonic Mach number, but you will get a supersonic Mach number. But probably here also, because the Mach number itself is 1.27, it is possible that you don't get a very large error. Let me check how, or I don't have that number with me. You can try that, okay? I don't have that number with me. That is something that you would have to try. Okay, finally, with this 10 atmosphere, this is gonna give you a good enough large error, and this you forget, it's hopeless. It's hopeless. Okay, so as your strength of the shock increases, you'll see that these formulas break down very fast. Okay, they break down very fast. So this was something that I wanted to just tell. Okay. Guys, can I just take a 40-50 second break? I'll just go use the washroom, fill up my bottle. I'll come back. So just stay tuned.
Okay, sir.
I'll
Okay.
just come back. Yeah.
Yes.
I'll just, yeah, I'll just come. Okay. So you guys are there? I
Yes,
guess.
sir.
Yes. Yes.
Okay. So, before I again start something new, I think that is gonna take time also. You have any questions from video lectures or anything you wanna discuss? Or should I go ahead with the thing I was gonna plan? I had planned, I meant. I guess not. Okay, fine, let's get started then. Uh, Fine. Also, have you guys been taught this Rankine-Hugenoid equation in the video lectures?
I think I don't know about Rankin Huguenot, but sir had discussed about Huguenot equation, the E1 minus
Yeah,
E2.
Hugenoid. The Hugenoid equation is the thermodynamic equation of a normal shock. Is that what you're saying?
Yes, yes,
Okay, then
yes. The
fine.
E1 minus
Okay,
E2 equals yeah,
fine.
that one.
Okay, so now let's come back. Let's go back to something that we had discussed in the very starting of the lecture. So, what all have we tried to, what all have we answered till up till now from today's thing? There was few discussions that we had. Where is this? Yeah, these are the parts we answered. Something that we did not answer is some. We'll look at this. Okay, we'll look at this. Yeah, what do you mean by weak shock? Do you guys know what a weak shock is? Do you guys know what a Mach wave is? Maybe you'll get to learn this in the future, in the coming weeks. Anyways, let's answer this question. Can we have a shock in subsonic flows? Deepti, do you have an answer for this? So Pranav answered it like this, that he said that we cannot, but he does not know how to explain it. He can't explain it like just he can't tell why there are no shocks in subsonic flows. maybe we can put it like this: why are there shocks in the supersonic flows? That is one way to answer the question. But again, why? What part of subsonic flow are we missing? Uh, what part of supersonic flow are we missing in subsonic flow that shocks don't appear there? There's a qualitative answer to it. There is also a very beautiful answer to it, I guess. Yeah, it's very technically satisfying.
I am confusing, sir. In subsonic condition, means shock is formed whether there is a sudden change in the flow properties. In subsonic condition means it's maybe not with any changes.
What changes?
Like,
What changes are there in supersonic flow?
Means there will be the sudden change in pressure, temperature.
But okay, very interesting. Why do normal shocks form in the first place? What like suppose there is a supersonic flow flowing, right? Um, there's a supersonic stream that is going in atmosphere. Will it always form normal shock? Why? When does a normal shock get? Uh, how does it come into origin? Why? Like, what is the genesis of a normal shock?
So
It's
in
a
supersonic
good. It's
condition,
a
we can't say either it is a normal shock, either it can may form a oblique shock also. Based upon the
yeah.
object shape, based upon the object, we can say either it is normal. I'm not sure.
But does it always have to be an object? So, for example, if there is an object, does it mean that there is gonna be a shock there?
Yeah,
So in presence of an object in a supersonic flow, there is gonna be a shock. That is
yeah.
what you're saying. I guess you're correct only. I don't know if you're making a wrong statement or anything. I think you're making a correct statement. But what is it about that body, or what is it about that object that is making giving birth to shocks? What is it?
Means there will be it's generating the velocity greater than the speed of sound.
No, that is the upstream supersonic flow. What is so?
Right.
Okay, let me just simply try to answer it. I don't know if even I am able to like even if I can answer it or not. I also thought about it, but the thing is, if downstream of some place, uh, there are conditions that require subsonic flow to exist, then
Yeah,
you will
after
get
the
a
shock,
normal shock.
the flow will be after the shock. There will
Yeah.
be the flow is always subsonic.
Yeah, but the thing is that the normal shock was there because the flow around that object cannot be supersonic. So, for example, if there is a if there is a large angle deflection or corner, uh,
Hmm.
the flow cannot be supersonic. It cannot just be supersonic in around that large wide corner. So flow has to be subsonic so that it can adjust to this change in deflection or something. For example, if there is a blunt body, again around
Hmm.
this blunt body, the flow cannot be supersonic. It has to be subsonic. That is why there is a normal shock upstream of it. So it's again philosophical, but anyways, uh, but the point is, there's a very interesting result that we can see, uh, especially in the case of an ideal gas. So I'll just read it out for you. Uh, okay. One
Sorry
more
to
thing.
interrupt.
Yeah, yeah. Go
Uh,
ahead.
means means explaining why a normal shock means. I just wanted to ask that can we explain like why normal shock occurs by this explanation that there is an object, so there is if there is supersonic flow, the
Hmm.
supersonic flow starts, it collides with the surface, and
Mm-hmm.
it comes to a stagnation. So around or on the surface, it is
Mm-hmm.
this the flow is the flow gets obstructed, and
Yes.
so it forms something like a wall or something, and
Okay.
it decelerates so much that the flow which is coming like uh, just before that, that gets
Hmm.
decelerated due to the flow which is downstream.
Yeah.
And so that's how a chain occurs, and we get a normal shock, and there is an equilibrium, and at in this equilibrium state we get a stationary, a normal shock. I don't think I'm able to put it into words what I'm
No, you
imagining.
did it very well. You did it very well. Uh, See, your intuition is quite correct. There are a couple of things I think you might already know as well. I don't know. But possibly one way to articulate what you are saying. Uh, well, there are few things that if you think about, you will make more sense. So the first thing is you're gonna soon read about traveling shocks, so moving shocks. Okay, there you will realize that actually shocks are supposed to move. Okay, shocks do not just simply stand anywhere. They are not stationary as such. The shocks are not by inherently stationary. The reason they are stationary is, or the reason we are studying stationary shock is that they are the simplest to s- introduce. Okay, the reason they remain stationary, they stand somewhere, is the fact that the flow upstream is supersonic, and it is at such a high velocity that the shock cannot move upstream. It wants to move upstream, but the velocities are so high that uh, the speed of maybe the no shock is being cancelled out. It,
Yes,
again, I'm
yes,
not
I think
technically
I was trying to say that only. Like,
great,
there is a
great,
shock which is formed near the surface and it moves upstream, but at a
great.
certain point it stops. So it's a detached shock like that.
Yeah. But the thing is, it's not the shock that is getting formed. That is also an interesting. So that is something I wanted to again. That was the second part of my like our discussion. I wanted to just say that shock forms by accumulation of compression waves. So what happens is again I'm speaking all in philosophical sense. Uh, Not very technically accurate. You have to do it, you have to mathematically do things to see how it goes. And you're gonna learn this in couple of weeks. You're gonna look at compression waves and how they form a shock. So compression waves go ahead and coalesce and form oblique shocks or uh, normal shocks. The thing is, suppose you think about this, okay? In subsonic flows, the presence of the nose of a body is felt at the speed of sound. Now, because the speed of sound is so high that the flow very smoothly turns around this body, because it's so high that the presence of this nose is felt everywhere, and it's felt at infinite speed. For incompressible flows, for Mach number less than zero point 0.3 or Mach square less than zero point 0.1, uh, yeah, zero point 0.1, you get this. You can consider that the disturbances travel at infinite speed. Okay. Now think at a good like what is physically going to happen. Suppose there's a fluid particle which gets hit by this nose. There, because its velocity is going to decrease, there's going to be a pressure rise, right? This pressure rise, this and there will be a local pressure in equilibrium because upstream of it pressure is something else. But now because this fluid packet uh, has been decelerated a little bit more. I'm talking about when the equilibrium is not set. I'm talking about in the sense in the unsteady part of it. There is no steadiness there because we have been dealing with then steady conditions. But consider that flow has just started around this body. What happens then? So what will happen is the pressure is just suddenly increased near the nose, and that pressure will propagate at again speed of sound. Okay, it will start propagating. So this pressure wave the more the pressure increases, there will be continuous waves that are gonna go because the flow is supersonic. These waves are not gonna travel much far. Okay, they're gonna I don't know what is gonna happen exactly, but I would have to look at it. But what exactly is gonna happen is what I know is gonna happen is that there will be a series of waves that are gonna go. The first wave will be slower than the second wave. The third wave will be even faster, and so on. So what will happen at some point, all these waves. So the first wave is a little slower. That is something that you will also look at in the course later on. The first compression wave will be a little slower. The second compression wave will be a little faster. Third compression wave will be even faster. So what is going to happen is they're going to collide into each other, and that is how see every compression wave has a small pressure rise. It will have a infinitely small pressure rise, continuously increasing this small infinite similar pressure rise each wave will have. Once they start getting coalesced, this infinite small pressure rise will keep on accumulating. They will keep on accumulating as long as that there's a steady state reached finally, so that P2 and P1 get settled down, and then at that when this accumulation of delta P starts happening, you'll see that the normal shock will get formed because they have now collapsed and the delta P's have added. So you'll see that P1 increases directly to P2 in a very small distance. The thing is that this is all very like this is a model. The normal shocks are not infinitely thin. In reality, they have a thickness, and there are a lot of things that are going on. In fact, if you look into real scenarios, there are a lot of shocks. Normal shocks is just an idealization in some sense. You do see them. It's not that you don't see them, but it's a very ideal situation. So you can't say like it's a model problem. You understand? Like a spring mass system. No spring would be like F equals to kx. There will be some other component, some higher order terms also. So but this compression wave analogy is something that you will look at. So that compression wave correlation is how shocks are formed. So that is something I could have like I could add, and I know how like what is happening. So that much I know. So I think that's it. I don't know if anything else I can add. Did you get what I said?
Yes, sir. Yes.
Did,
Yes.
okay. So fine. Now okay. Now okay fine. So we know upstream of the shock, there is some pressure which increases downstream of the shock. Is it possible to have an expansion shock? Can we have, suppose there is supersonic flow and you suddenly expand it rather than compressing it, you expand it suddenly so that you can get an expansion shock. Is that possible? See, these are questions. I don't know even if that these questions are gonna come in your exams or anything, but it's nice to discuss. These are like I guess your NPTEL problems are not that tough. What do you think? Are they tough to be discussed? Like these are numericals, right? I thought like this would be a good discussion rather than
No, sir. No,
having
it's a
solved.
good. It,
Yeah. So I don't know if this is not gonna help you much in the exams, but I think it's still some good discussion. But what do you think? Are you gonna have some expansion shocks? Can you have some expansion shocks?
sir, expansion shock means the after the shock, the Mach number should be greater than the upstream condition, right?
Yes. Yes.
So it's based upon the I'm not sure. It's based upon the body shape, object body shape to achieve that Mach
Interesting.
number.
Interesting. But I think you're talking about expansion fans. Are you talking about expansion fans or are you saying expansion shocks only? Even I don't know about
Expansion.
expansion shocks much. But the thing is, I'll just because I read this in one of the book, expansion shocks are impossible in an ideal gas. You'll see why. I'll show you why. But they might occur in real gases. So our intuition or whatever we have learned, we might think that normal shocks are the only reality that can happen, because no, before getting introduced to normal shocks also, nobody would believe that there is this something which can like there is a lot of normal shock is a discontinuity. We don't see any discontinuity in normal fluid dynamics. So nobody would believe the existence of normal shock upfront, right? Similarly, there are expansion shocks and all also. In a perfect gas, it won't be there. Ideal gas, it won't be there. But it can happen. In theory, it can happen in a perfect gas, in a real gas. Just a comment I read in the book, so I just mentioned it. Anyways, fine, fine. Okay. One more thing which I wanted to add is uh, because we have been dealing with only the ideal gas, right? This perfect gas, constant CP, constant CV, and ideal gas law is uh, ideal gas law is satisfied or followed. I'll tell you what I wanted to say. That beautiful answer of why shocks cannot occur in subsonic flow. We'll see if we solve for the entropy change across the normal shock, we'll see that in subsonic flows, a normal shock will decrease the entropy, which is against the second law of thermodynamics. So we'll see that. I'll show it to you. I just wanted to give you a teaser. So we'll see that. I don't know if we'll do that in today's class. We'll do it maybe next class. But there are two things I wanted to again like discuss with you. Does entropy not decrease in thermodynamics by like when I say that entropy is decreasing and that is violating the second law, am I making sense? Because uh, does entropy not does entropy never decrease only in thermodynamics? And does it always violate second law whenever entropy decreases? What do you think?
Yes.
Yes, what? Like entropy never decreases, is it?
Based upon some assumptions, we can say it's not decreases.
Based upon what?
Means we are considering the flow as an ideal.
Flow is isentropic. Okay, flow is isentropic.
Yeah.
No, but normal shock is also so what is normal shock? Is normal shock isentropic?
Yeah.
No, it is not.
Uh,
We
Normal shock is not isentropic, right? So given that hello, guys, am I still audible and is the connection
yes,
fine?
yes, yes.
Yes, sir.
Ah, so I was just saying, Pranav said that normal shock is not isentropic. So and what is the entropy increasing there or decreasing?
Increasing.
Increasing.
We we
Huh. Yes, you're saying something.
increasing.
Increasing. It increases. The fact that in subsonic flows, a normal shock would imply that entropy decreases. Why does it violate the second law? Can anyone tell me that? Pranav, maybe you? No? You can say no. That's okay. You can just tell, sir,
No, sir. No,
like you. No?
no, sir.
Ah, okay. Let's
Because
break. Huh.
I think it means uh, in a subsonic flow, if
Forget about subsonic flow.
okay,
Let's
no, never mind.
yeah,
Sorry.
let's break down the problem. Let's break down the problem. What is the mechanism of entropy? What what does the second law say? Does the second law say that entropy of a system will never decrease? Is that what the second law is? This you guys can
Uh,
tell, right?
Yes, it never decreases. Means yes,
So
it
you're
never
saying
decreases.
it no, you're saying entropy. No, no. What are you?
Hello. I think
Okay.
the
So
there is
basically, there's a
some.
small catch there. I'm trying to just trap you there. See, second law says that entropy of the universe can never decrease. The point is that if a system plus surrounding is taken as a whole, the entropy of an isolated system is never decreases. Its second law says entropy of an isolated system never decreases. Okay, what does an isolated system means? No mass is gonna leave the system, no energy is gonna be exchanged or transferred to the system. Is that fine? Do you guys agree?
Yes.
Yes.
Another thing, there are two mechanisms of entropy decrease. There are multiple mechanisms for an entropy increase, but there are only two mechanisms for an entropy decrease. Can you guys tell me what those are? I'll tell you. You were gonna say, or should I go ahead?
No, I'm not sure. I think you should
Ah,
go
okay.
ahead.
Okay. So there are two ways. Either you cool down the system, right? Think about it. The TS plot, the saturation dome. Suppose from the superheated state to the saturated liquid, entropy decreases, right? Because you're cooling the system, right? You remember that, right? The TS plot. Let me draw that.
Yes, yes.
Right? Entropy decreases. There is one more way. So one way is cooling the system. This is SG and this is SF. So if you cool the system, you know that you're gonna decrease the entropy. There is one more way, and that way is to remove mass from it. So suppose there is some tanker, some volume is there. You remove some mass from it. You know that you have and mass has some entropy, right? This suppose we are on an isobar. It has a specific entropy, right? It has a specific entropy. Some mass will have a entropy with it. If you remove mass, that much amount of entropy multiplies the mass you have removed, will get removed from the system. That is what the second law says. There are only two mechanisms of how entropy can be decreased. E- I'm not talking about increasing. There are multiple ways of increasing it. Decreasing it is there are only two ways. Either you cool it down or you remove mass from it. And that is why when we say second law, we say isolated system. Both of these things can't happen because energy cannot be exchanged, mass cannot be removed, and that is why we know entropy is only gonna either increase or remain same. When does it increase? Because again, without exchanging mass or energy, you can't even increase the entropy by any reversible method. To increase the entropy in that case, you have to do some irreversibility in the system. So that is also something second law talks about. So here the catch I was trying to play was that obviously there is no mass exchange or mass removal. This is a steady flow process, right? When we talk about a normal shock, it's a steady flow process, right? So there is no discussion on mass removal. It's only a heat addition or heat removal. And we see that across a normal shock, normal shock is a adiabatic process, right? It's a adiabatic process. There is no heat exchange there. There is no work exchange. So there is no work exchange also. There is no heat exchange also. So that is why if across a normal shock there is an entropy decrease, it implies system's entropy is gonna decrease. The whole system plus surroundings entropy is gonna decrease, which is against the second law. Did you guys get what I said in the last few sentences?
Yes, yes, yeah.
Yes, yes.
Got it.
Okay. So now we are gonna so next time I'm gonna start by writing the expression for the entropy. We're gonna see how that comes around, and we'll carry on from that. Okay. So I guess yeah. So you guys can log out. I'll also leave. If you have any questions, you can ask me.
So can I able to access the previous class? Means I
Yeah,
can't
yeah.
able
I
to attend.
guess. Oh, there's a I think there's a sheet shared with you, right?
Yeah, the sheet shared
No.
is, but it is only view only. I can't able to go through it.
That access I don't know how to, because access I also don't manage, but it has links,
Okay.
right?
Yeah, sir. Yeah.
So what you can do is I guess you can't copy the links. That is your issue,
Yeah.
isn't it? So what you do is you go to inspect. Okay. Every see I'll show it to you. Wait, let me do that.
Okay.
So let me see. You can do that. I think this is the one there. I can also view. You can open it, I guess. No, you can open it, I guess. Yeah, yeah. Even
Oh.
if you can't open it, even if you can't
Mm.
open it, what you do is you go to this inspect. This somewhere it will be inspect page. Here, no tools. Do you see inspect somewhere?
Mm.
Uh,
You can just
anyways,
press
let
F12.
F12, is it?
Yes.
Oh,
If you're on
okay.
laptop, then you could just press Fn and then F12
Okay, wait.
Okay.
because you may have
So
Fn plus
what is
F12.
where is FN, FN, FN? Where is FN? Okay,
Bottom left.
great. Yeah, okay. Yeah. So this inspect you do, and now yeah. Otherwise, you can I see you can access this thing. You can
I
just
think there is
click
a
on it.
copy button also in that pop-up.
Yeah, I think this is the one you guys can access. Or which is the one? There's a copy also, is it? This
That
yeah, you can copy also.
no, no, there is a copy button also in that pop-up.
Okay.
You
Okay.
just
So
hover over there. You can
okay,
on the bottom, sorry, top right corner of that. Yeah.
okay, got it, got it. This one.
I will check, sir. I will check.
Yeah, yeah.
Mm.
So fine, guys. If there are any more questions, I can take them.
No, sir. No.
Great. So
So in the
meet
next
you
week,
next time. Huh. Yeah.
we are also having a live session, right? Like we are having both, right? Problem solving and a live session in the next week. I think Professor Srisha Rao, he's personally going to take a
I don't
live
think
session.
he's gonna take. No. I don't think he's gonna be there. It is gonna be a recorded thing only, I guess. Not sure.
But
I'm not
they
sure.
said
Probably,
because they shared a
probably,
Zoom
probably.
link,
Okay.
that's
So
why.
probably
At
then yes.
24th, sir.
Yes, on
Then
Monday.
probably yes. Then probably yes. Then probably yes.
Okay, so
Because
we are having both, right?
yeah, probably.
Yes.
Not sure,
Okay.
but yes. If you've received the mail, yes.
Okay.
Yeah. So see you next time. Bye guys.
Yes, sir. Thank you.
Bye.
Thank you.
Thank you.
Thank you.